Now that we have defined about the quadrilateral and its different types of quadrilaterals, the most important of them being parallelogram, and various other quadrilaterals like square, rectangle, trapezium, rhombus, kite, etc. The most specific quadrilateral which we have discussed in the previous session and its varied properties was parallelogram. So let's see the other definition of how a quadrilateral can be defined to be a parallelogram, or how a parallelogram is defined, or when the quadrilateral becomes a parallelogram. So these are related to the property, another condition for quadrilateral to be a parallelogram. Other condition for a quadrilateral to be a parallelogram. So let's see the other condition. Now that we have defined the quadrilateral to be a parallelogram if its opposite base, or if the pair of sides of the opposite sides are parallel, then the quadrilateral becomes a parallelogram. Now let's define the other condition for a quadrilateral to become a parallelogram. So coming out with the definition, when the opposite sides are parallel, is how we have taken for line 1, line 2, line 3 and line 4 arranged in such a manner that it forms a closed region with its opposite base being equal, is said to be a parallelogram. Now we will try to change the definition into a more modified form. Let's see the definition, which stands for another condition for a quadrilateral to be a parallelogram. A quadrilateral definition. A quadrilateral is said to be a parallelogram if its opposite sides are parallel and equal. This is said to be the modified form of defining a quadrilateral to be a parallelogram. So a closed four-sided figure that is a quadrilateral is said to be a parallelogram if its opposite sides are both parallel and equal, is how we can combine the parallelity and equality for making a parallelogram or defining a parallelogram. So ABCD is a parallelogram if quadrilateral ABCD is a parallelogram if AB is parallel to DC, and AD parallel to BC. AD parallel to BC. Along with this, it must also satisfy the equality condition. This becomes parallelity condition, and the equality condition is that AB must be equal to DC and AD equals BC. Is how I understand a quadrilateral ABCD reducing to a parallelogram if it satisfies the parallelity condition. Parallelity and equality condition is how I understand a quadrilateral reducing to a parallelogram as another condition for a quadrilateral to be a parallelogram. The quadrilateral is said to be a parallelogram if its opposite sides are parallel and equal. That's how we understand the definition for quadrilateral reducing to a parallelogram. Now that we have defined a parallelogram and a rectangle as the special cases of the quadrilateral, let's see how a rectangle can be derived from a parallelogram. There's an interesting property which connects deriving a rectangle from a given parallelogram. Today's session is about deriving a rectangle out of the parallelogram. So let's take a parallelogram ABCD. Deriving a rectangle from a parallelogram. So let's see how a rectangle is derived from a parallelogram ABCD. So here is the parallelogram ABCD. Of course, the pair of sides being parallel and equal. Now, the two sides are parallel and opposite sides are equal. Now let's see how a rectangle is derived. Now as I have four angles, angle A, angle B, angle C and angle D. Now here I would like to draw a bisector for each angle. That is, for angle A, I take the bisector that is exactly at equal angle. I just extend this. Similarly, I take the bisector of angle D. Angle B. So here is the bisector of angle B, exactly cutting at equal angle. So here is the bisector for angle B and here is the bisector for angle A. Similarly, I have a bisector for D which I derive out here, and a bisector at C derived out here. So I have taken for each angle of a parallelogram a bisector, that is a line which makes equal angles on either side is what we call the bisector. So here I take a line which makes equal angles on either side. I take another line which makes equal angles on the other side, similarly at C and D. Interestingly, I see that each of the lines, line 1 and here is line 2 and here is line 3 and here is line 4. So these four lines try to intersect at four different points and it forms a region which is this. It forms a region which let me denote by PQRS. Now this region seems to look like a four-sided closed figure. Yes, the four lines, line 1, line 2, line 3 and line 4 intersect to form a four-sided closed region and which is called a rectangle. The bisectors of a parallelogram intersect to form a rectangle. It will have each angle is 90 and opposite sides are equal, is how I see the property for this. So PQRS quadrilateral PQRS, which is formed by the bisectors of the original parallelogram. Usually this quadrilateral is formed by the bisectors of each of the angle of the parallelogram, which is formed by the bisectors of each vertex A, B, C, D. Each vertex of the parallelogram ABCD is a rectangle. Is how I understand the property. The quadrilateral PQRS, which is formed by the bisector 1, bisector 2, bisector 3 and bisector 4, forms a closed-sided region which is called a rectangle, is how the property comes. Therefore, PQRS is a rectangle and each of the angles is 90 and opposite sides are equal, is how we understand the concept of the rectangle derived from a parallelogram. So any parallelogram whose bisectors are meet at four different points, that four close-sided region is called a rectangle. This holds for any parallelogram existing in the branch of mathematics. Rectangle derived from a parallelogram.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.